I want to talk about enzyme activity and kind of how we as scientists understand how enzymes work. Now, when we use models as scientists, there's a couple different types of models we can use. We can use physical models, which model kind of some sort of physical behavior. This is what we think this thing looks like. This is what the inside of a cell looks like, right? It's got a nucleus and an endoplasmic reticulum, and there's these ribosomes and all the things. Or we can have a conceptual model, which is more of modeling the behavior of a system. Now, when we're talking about enzymes, the models that we use are both physical and conceptual, but they lean more towards the conceptual side of things because there are so many types of proteins that can act as enzymes that to say that there's one model to explain the behavior of all of them is a little bit short-sighted. So we have to have kind of some broad strokes understanding of how these work, and that's what I want to talk about in this video today. So recall that enzymes are proteins, so made up of amino acids, that are biological catalysts. Now, a catalyst is something that speeds up a chemical reaction or a chemical process without itself being consumed in the reaction. So the catalyst comes in, it does its thing, speeds up the reaction, usually by lowering the activation energy, which is the amount of energy, the minimum amount of energy required for that process to occur. So it brings that energy down, and then it gets spit out the other side whole as it was, and then it can go on to catalyze something else. So these catalysts, or these proteins that act as enzymes, can be used over and over and over again and can catalyze a number of different reactions. Now, the protein types, we've said that there's a lot of different types of proteins, and in general, chemists don't like to make blanket statements about things because there's always an exception to everything. But the proteins that are enzymes are globular. They tend to be water soluble. These are important because, we're happening in an aqueous environment of some sort of biological organism. Now, how important are they? How much of an impact do they actually have? Well, they're hugely important. There's really no metric to explain how important enzymes are and the proteins as enzymes are in biological processes. There are some things that could happen spontaneously, meaning that the process is going to occur without any sort of outside influence, but that would never happen in the span of a human's life, right? So it could take more than 100 years. It may happen on its own, but it would take more than 100 years. And these catalysts, these enzymes, can speed up that process to where we have these things doing those processes many times per second even. So it's incredible. It is so hard to get your head around how important this is. There's a value that we use because, of course, scientists like to measure things. So there's a value that we use called the turnover number, which is the maximum number of substrate molecules that an enzyme acts on per unit time. So, as scientists, we use SI units. The unit of time that we usually think about is seconds. You can talk about time in a number of different units, but seconds is the go-to. And maximum number of substrate molecules. A substrate is the thing that the enzyme is acting upon. So it's that molecule that is being acted upon by that enzyme. So it could be any molecule in there. So it could be a free radical. It could be a carbohydrate. It could be a nucleic acid. It could be whatever. And these substrate molecules, then the maximum number of them I get per second or per day or per year is my turnover number. So most enzymes, and again, this is just kind of mind-blowing, most enzymes have a turnover number of about 10 to 1,000 molecules per second. So this is happening all over your body at 10 to 1,000 molecules per second. So these enzymes are systematically the most important thing happening in your body to make things work and to make functions in your body work. So when things break down in this process, then it can cause all sorts of chaos. Okay, so how does it work? Well, the normal model is to say, well, we have an enzyme, and again, this is very broad strokes general. We have an enzyme, and we'll just call that E, and a substrate, which we said is the molecule that this thing is acting on. And then they're going to react together chemically. It gives a chemical pathway for these things to interact, and that could be through intermolecular forces. It could be through actual chemical bonding. There's some way that the enzyme and the substrate are reacting together to form this complex. So they come together in this complex, and then there's some sort of rearrangement, and we have a new thing now. So it's no longer the substrate that came in. We have a product now that comes out of this in some sort of different form, but it's still attached to the enzyme. So now we have an enzyme product complex, and then what spits out is an enzyme plus the product. Now note that the enzyme through this remains unchanged. So it did something to react with it, but it comes out the other side looking exactly the way that it came in. It's the substrate that's being acted on. So we have a substrate on my kind of reactant side of this process and a product on the product side. So this is the general model that we use to understand enzymes and substrates. And visually, there's a couple different ways we can think about this. The traditional way is what is called the lock and key model. And this is very much kind of, in my mind, the Pac-Man model. So we have kind of, here's our Pac-Man. And then this is my lock, this is my enzyme. And then the key part is going to be whatever the substrate is. So the substrate has to fit into, let's make it kind of ice cream cone looking. That's adorable. Okay, so there's my substrate. So this substrate has to have the right shape. Remember, in biochemistry, the name of the game is that the structure influences the function. So there has to be a perfect fit between the lock part and the key part of my enzyme and substrate. And so when I put them together, then I have, here's my, let's make it kind of up like this. And then I have my ice cream cone in there. So here's my substrate, my enzyme. This is my enzyme substrate complex. And then some sort of rearrangement would happen, and then this thing would spit back out. I'd end up with my enzyme at the end here as it started after my rearrangement, and then my substrate maybe comes out in a slightly different form. This is now my product. Okay, so again, kind of Pac-Man-y. I know that this is highly sophisticated artwork, so hope you can keep up. But the lock and key model is a little bit dated because it really implies that there's this static nature of an enzyme and the substrate just kind of goes in there and sticks in there, and then something happens, right? And that's kind of a black box. And then the enzyme spits it back out, and then we have something new that comes out of it. We know now, as we've gotten better and better technology, as we're able to study these in more and more detail, that it's not necessarily a lock and key, although this is a good way to kind of understand sort of the process. I think it's a good visual tool. But what really happens is what we call the induced fit model. An induced fit means that we could start with the same Pac-Man here, but maybe it's a more of a broad active site. So the enzyme here has a larger place where that substrate can bind, and that's called the active site. Should have probably put that on the other one. So this is more of a generalized active site. There's still it depends on the protein, it depends on the enzyme, but there's varying degrees of what is called specificity. So specificity is how specific that enzyme is to the particular substrate, or how specific a substrate has to be for a specific enzyme to work on it. So for example, does the enzyme work for all carbohydrates, or does it only work for disaccharides? Does it work for a specific type of amino acid? So maybe it only works on alanine, but it doesn't work on any of the other amino acids. So the specificity of different enzymes is going to influence how this process works and how specific that active site is, because that active site is really where all the magic happens. This is where there's all the stuff that's going to trap that substrate, that then it's going to do whatever chemical and physical manipulations it does, and then it'll spit it back out. So that means I could have something like, here is my substrate, and now this substrate is going to come in, and my enzyme substrate complex then is going to be something to which the enzyme does some sort of physical rearrangement. So let's kind of do this kind of operation. So here's my substrate, here's my enzyme. So this is that induced fit piece. So induced means that it's kind of forced into like an induced dipole on something. So there's a dipole where there wasn't a dipole before. So induced fit is there's a fit where there wasn't a fit before. So this thing can come in based on what it is and the specificity of that particular enzyme. Then that substrate comes in. There's a rearrangement of the enzyme somehow to get that substrate in there. and then the enzyme does its magic. It's not a very scientific way to talk about it, but the enzyme is going to do some sort of chemical or physical process that allows for whatever products to form out of this. Let's say there's 2. So maybe it cleaves this substrate a little bit, and then this thing will let go, and now I still have my enzyme in the form that it started. So there's that generalized active site again, and then I have the 2 products that come out. Okay. So that's more of an induced fit. This is more the way that we understand enzyme activity these days, is that the active site isn't super rigid. There's some flexibility to it, but that flexibility depends on the specificity of the enzyme and kind of what the substrate is that it's acting on, what the commonalities of the different functional groups that are on the substrates, what exactly it's supposed to be doing. Is it cutting things? Is it adding things? Is it oxidizing or reducing things? Is it just creating an environment for these things? So this active site has a number of different roles. So let's talk about that for a second. So what the heck happens at the active site? Which feels a little bit like a black box. And I feel like, especially at an introductory level, we oftentimes just say the active site and the magic happens. But there's multiple things that could happen chemically and physically at the active site. So these are kind of the ways that it works, I would say, if we were going to talk about these different categories. So there's really multiple options. You could have something where the proximity of 2 functional groups is forced, right? So we put this substrate into the enzyme, and it brings things closer together that weren't normally closer together. So we have maybe a long chain of something, and we put it in the active site, and now the 2 ends of it maybe are closer in proximity, and now those 2 ends can react in a certain way, for example. So they wouldn't have normally reacted, but we're putting them closer together. We're forcing them together. We could also change the orientation of things. So if we're reorganizing the conformation, maybe we're twisting, maybe we're bending. So we're kind of reorganizing this conformation or the orientation of the molecule. And then again, that's forcing things to happen. Usually when we're talking about enzyme activity, we're talking about bonds breaking or bonds weakening through the enzyme so that they can break. It takes lower energy. That's that lower activation energy piece. It could also just provide catalytic conditions. So maybe we have some acidic groups or some basic groups, or we have some things, some redox kind of oxidation reduction kind of potential in these active sites. So it's creating the catalytic conditions for the chemistry to occur. So we needed a more acidic environment than we have under normal pH. We have some acidic groups in there. So if we can get that in there, then we can cause some acid-base chemistry to happen. That causes the product to come out in the way that we need it to come out, etc. And the last thing is that just kind of energy barrier lowering. That's really all of them, but in some of them it's doing it in a very intentional kind of way. And again, that's usually by weakening these bonds. So they could be through any combination of these. We're shifting and bending, we're putting things in closer proximity so that they react. Collision theory in chemistry says that things have to bash together in order for chemistry to occur, so that proximity is going to matter, right? We get things in closer proximity to each other, we change their orientation, we give them the right conditions, then that all lowers the amount of energy that is required for these reactions to occur on their own. Well, or not on their own, they're facilitated by enzymes. Okay, so that's what's happening at the active site. Again, this is very broad, very general. We're talking just kind of how enzymes work as a general rule. If you want to look up specific enzymes, then you can really get into the nitty-gritty details of what does the active site look like, what kinds of things is it providing, what substrate is it acting on, and then what is the product that we get out of it. And those are all good questions to ask about enzymes, and there's just so many you could spend your lifetime studying them. Kind of cool. If you have any questions on this, don't hesitate to reach out. Otherwise, I'll talk to you again soon.